Oh man, it's time for some financial models, ladies and gentlemen. You're like, hey, when am I ever going to use this math in real life? Right now, all right? We're going to have your money making money and making money off that money that made money off that money and made more money. We're talking about compound interest with that. All right, so I had to find some, of course, some money memes. We've got investing, the dude from the History Channel that's always talking about aliens. A classic, Toy Story, wonderful. We've got a dog as well. My advice is to invest in tennis balls. They have a high rate of return. And then I love me some Jack Black from Nacho Libre when my friends start talking about investment opportunities and stuff. And, of course, I love tacos. How many is that in tacos? Fantastic stuff. Okay. Let's get on to the math, shall we? We've had a good laugh. Now it's time for the real fun. All right. So you may have seen these formulas before in previous classes, right? There's also one that's called simple interest that we're not really going to get into. I'll show you that in a sec. But these are the ones we're going to focus on. So we've got interest for growth and decay. We also have our compound interest formula, okay, where R is our rate, T is our time. That's pretty straightforward. N, and we might want to jot this down here. We want to jot down that N is the number of times we compound per year. Okay? And then the last one, we have a compound interest formula for compounded continuously. So if a problem says that it's compounded monthly, we're using formula number 2 here. If it says that it's compounded continuously, we're using this third one here, the A-PERT, hence the shampoo bottle here. Hilarious. All right, if something's just growing or decaying, that's number 1 there. Like if we're saying that the value of a car is declining at 2% a year, you could use this top formula. The ones that we're going to work with today are 2 and 3 for the most part. All righty, let's go. You know what I decided? I'm going to throw in the A sub 0, or P, because you can see that in these formulas here. That's our starting amount. Sometimes they refer to it as your principal, right? Your first investment, what you're starting with. Your account is $1,000 to start. That's your A sub 0 or your P. R, that's our rate, okay, as a decimal, a percent written as a decimal. And then T, that's our time. Okay, so now that we have those all written down, I think we're good to go. If you need to pause to jot that down, go for it. You're definitely going to need these formulas written down nice and organized because we're going to use them a lot. Yeah, the one that we're not really going to cover in this class is our simple interest formula. You might use it in maybe a finance class, something like that. But we won't really deal with this one. You may see it come up in other aspects, but we're going to focus on the compounding ones, okay? All right, our first example, we got P. Diddy. I hope you guys know who P. Diddy is. He knows that it's all about the Benjamins. Those are $100 bills. As you can see there, he is counting the money, and look at that now, a dollar bill. That's why it's so confused, because he knows it's all about the Benjamins, as you see there. That's a pretty awesome candid photo. Anyway, so he takes investing very seriously. How much more will Diddy make if you alter the compoundings of a $1,000 investment? That's 10 Benjamins. What would happen there? So if we go from compounded monthly, compounded daily, and compounded continuously, what's going to happen? And we're going to do it over 15 years. We should see a bit of a change here. Well, let's set up the first one. I'm going to go with green here. So we're talking about money. Then again, we're talking about money pretty much the whole time. So I'll switch up colors. So we want the amount of money after 15 years. So A of T, that's not a multiplication problem. That's saying the amount of money after 15 years. And our starting amount is $1,000. And then we have 1 plus our rate here. 7.5% compounded monthly. So 7.5% as a decimal would be 0.075. If we're compounding monthly, how many times is that? That's 12 times. And then the other n up here would be 12 as well. And our time, we're saying, is 15 years. So we're going to plug that all into our calculator. All right, so let's pop those TI-84s out, or TI-83s, whichever one you have. All righty, so I've got typed into my calculator. Be very careful as you're typing them in. This one, the functionality isn't as nice as some of the newer 84s, where it will actually put a little exponent, right? So I have to put parentheses around that 12 times 5. Otherwise, it will raise it to the 12th, then multiply everything by 15. Okay, sorry, 12 times 15, not 5. So otherwise, we got it all good here. I don't need to put parentheses around the division here because division is going to take precedent over the addition of 1 plus that. So if I hit enter here, that'll tell me how much money that account's going to be worth after 15 years, sitting at 7.5% interest compounded monthly. Wow, that's substantial, right? That's more than triple the initial investment. Just having the money sit there, because that money is making money off the money that made money and making money off that money that made money prior to making that money. It's compounding. Okay, so what about if we compound it daily? Well, what's going to change in our formula? Well, now instead of compounding 12 times per year, we're compounding 365 times per year. So that 12 is going to change to a 365. So let's type that in. Now, I don't know if this one, darn, I can't arrow up and change it. But if you have one of the newer ones, you can arrow up, hit enter, and it will bring down what you had up there. And then you can just replace the 12. Okay, sorry, I can't show you that with this one here. I'm just going to retype it in, all right? All righty, so as you can see here, we have a little bit more, right? It's $3,079.86 just from the extra compoundings. Now, what occurs here is we take this interest rate of 0.075, we divide it by 365 and get this really tiny number, but they apply that tiny interest amount every single day, okay? Which is where we have the exponent there of 365 for 15 years. So if it was annually, you wouldn't have a 365 here or here, and it would just be compounding the 0.075, the 7.5% interest once a year. But now we're doing a small interest rate, but we're doing it 365 times in a year, so that adds up to quite a bit more. Well, in this case, about $10 more. But as you can imagine, the more money, the more time, the bigger the change. Now let's take a look at continuously. So I'm going to type that one. Actually, we'll write that one out because it's a different formula. We have A PERT, right? That's what that one is. So the amount after 15 years, and then our principal, our initial amount of money is 1,000. E to the R, which is 0.075 times the 15 years. That's what we're going to plug into our calculator. Let's go for it. All right, let's see what we got here. When I hit enter, I got $3,080. Woo! So there we go. We've got our three answers. We have $3,069.45. We have $3,079.86, and then $3,080.22 when I round. So as we can see here, the more times we compound, the more money we get. If everything else is the same, the interest rate's the same, the time period's the same. More compounding, mo better, right? Better with more compounding. If you're the one that's making the money, right? You don't want to be paying somebody back and have your interest be compounding multiple times, right? You'd want the less compounding in that situation. But if you're the one making the money, more compounding the better. Nice. All righty. Let's keep moving and grooving. All right, next example here. We got T-Pain. He wants to buy a boat. He wants to write a song and film a music video with about being on said boat, okay? And this is his 5-year plan, right? So he's going to, not right now, okay? He's planning out his future. This is his 5-year plan. If the boat will cost $15,000, how much does T-Pain have to invest now at 3% compounded monthly to achieve this? Okay, so T-Pain, he's not messing around. He's a planner here. All right, cool. Let's do this then. So we have $15,000, or that's the final cost, right? He wants to know how much he needs to invest now. So what we're really trying to figure out here is the A naught. We're trying to figure out that guy right there, right? Okay, so let's set up our equation. I'd have $15,000. I don't know what that is. I'm actually out, so we'll say that's A naught. Okay, and then 1 plus, I know my interest rate is 3%, which would be 0.03, divided by, and it's compounded monthly, so that's going to be a 12 right there, and then raised to the 12 times, this is 5 years he's planning out. So now I got to do some solving, right? Well, I mean, what could we do here? I noticed that all of this right here, these are just numbers here, right? Couldn't I just plug that into my calculator? Let's do that. So I just did the inside portion here, just so we'll break it down a little bit. This ends up being 1.0025, and then 12 times 5 is 60. Okay, so now we can maybe see a little bit clearer that it's just going to be a nice number. If we raise that to the 60th power, we get this super duper long decimal, 1.161616782. Oh my goodness. Now, if I want to solve for A naught, right, and I have a number times that A naught, I would need to just divide by that on both sides to get my final answer. So I'd be doing 15,000. This thing's running a little slow here. There we go. 15,000 divided by, and I would divide by that nasty decimal right there. But how do I don't want to type that all in, right? I mean, that just seems kind of like a lot of work. Now, on the newer calculators, you can just arrow up, and then it will it'll allow you to highlight, select it, and it will just put it in the last place that it was. On this one, since it's a slightly older model of calculator, so if one that you're not able to arrow up, even some of the 84s, like this one's an 84 emulator, does not allow you to arrow up. What you can do is you see this little ANS down here with the negative sign. If I hit second and then that, it'll say ANS. That will be the last answer that you used will go right there. I can divide by that and hit enter. That way, we're living by the laws of YORO. You only round once at the very end. If I round throughout the problem, it's going to become less and less accurate. We don't want that, okay? So now that I have that answer there, boom, that's the start. That's the amount of money that T-Pain needs to invest in order to have his boat 5 years from now. In order to fulfill that 5-year plan, we've got $12,913.04. Okay. There it is. Nice. I like it. Good stuff. Applying some math. This is fantastic, right? Let's keep going. So we've found just what happens when we're compounding, different amounts of compounding. Now we've solved for a missing starting amount of money. Perhaps we could solve for rate or number of times we need to compound, maybe time. I mean, who knows? The sky's the limit here. Alrighty, so now we got P. Diddy once again, but he's convinced the Notorious B.I.G. to get in on the investment game. Now, Notorious made an investment at 6.5% interest compounded continuously. Okay, so that's the A PERT. A of T equals P, E raised to the RT. How long will it take to triple the investment? Now, what seems weird here is we don't actually have the amount of money handy. It doesn't say what the initial investment was, so how do we know what the triple would be? Well, here's a fun fact for you. It takes, given everything else being the same, it would take the same amount of time for $1 to triple to $3 as it would for $1 million to triple to $3 million. Given everything else, interest rate, number of times compounded, all that remaining the same, $1 to 3, 1 million to 3 million takes the same amount of time. So what we'll do is we'll just say, well, if my initial investment's 1, then my new one would be 3. So I'll have 3 equals 1 E raised to the 0.065 T. Okay. So I'm trying to figure out how much time it takes to go from $1 to $3, because that's tripling, right? If you want to put $1 million in, that's fine too. It's going to work out the exact same way. So if I divide by 1, that's just gone. It's just really 3 equals E to the 0.065 T. Now, I'm trying to solve for an exponent. What can I use to solve for exponents? Well, I can use logs to do so. Now, either you can put this as log base E of 3 is equal to 0.065 T, or you could know that that's a natural log of 3, because that's just even a little easier to type into your calculator because you have a special little button, right? You got a special little button there. All right. So now I just have natural log of 3, which is a number, equals 0.065, which is a number multiplied by T. If I have a number multiplied by T, how do I solve for T? I'm going to divide by said number, which is 0.065 All right, let's pop out the calculator. All right, so I got natural log of 3 divided by 0.065. That's going to be 16.9 years. Man, it's going to take a little while to triple, but hey, it's all good, which is a little bit longer than I think one of the earlier ones we had, 7.5% interest, and it tripled after like 15 years. So, that makes sense if we think back to one of the other problems. So 16.9 years. Okay, now Notorious realizes mo money, mo problems, mo math problems, that is, and wants to compare that investment to how long it would take if the same investment was just compounded monthly. So rather than compounding continuously, we want to compound it monthly. So what formula are we going to use? We're going to be using our compound interest formula, which is boom, there it is. All right. So what parts do we know? I know, so the A of t, the amount after a certain amount of time is going to be the 3, right, because we want it to triple. Our initial amount is just $1. We really don't even need to write that, but we will, just to show the 1 and the 3. My rate, again, is 0.65. It's compounded monthly, which is 12, and then raised to the nt, so that's 12 times t. And now we can once again solve this. All right, so I decided to plug the what's inside the parentheses there into the calculator. We get 1.005416667. Real long number there, right? So that's what I've got going on as the base of that exponential side of the problem here. So I have 3 equals 1.005416667 raised to the 12t. So how do I solve for an exponent, right? How do I solve for that missing exponent? Well, remember, logs are exponents, so if I write this in log form, well, then I can solve for my exponent. So let's do that. I would have log base, and it would be 1.005416667 of 3 equals 12 times t. And I know that log base something of something is just a number. So then I'd finish this out by dividing by 12 to get my t. Now, this seems a little to try and plug into your calculator, right? So in order to do this more efficiently and accurately, we don't want to round. We don't want to put in a rounded value, and we'll show you why here in a sec. But when I go to my calculator, I already typed that part in. So what I'm going to do is I'm going to hit this button here, store. So it's going to take the answer, the one that I just had, and I'm going to choose the letter B here because log base B, right? That makes sense. I'm going to use the letter B. And when I hit enter, anytime I use this letter B here, alpha B, it is going to plug in this number for me, okay? Nice and accurate. So if I'm evaluating this, if I plug this into my calculator, as you know, unfortunately, this one doesn't have the alpha math feature or the log base feature. So I'm going to have to use change of base, which is log of 3 divided by log of, well, I stored it, right? B. And when I close that out, hit enter, I get 203. And then I have to divide that by 12, as we said, to solve for t, to finish solving for t. And what do I get? 16.94 years, which is a little bit more than the previous one. It was like 16.90 something years. So it is going to take a little bit longer when it's monthly, okay? So good comparison though, right? 16.9, about 9.5 almost. Now let's talk about what would have happened if I were to have done, if I were to have rounded it, okay? Even let's say 3 decimal places, which seems substantial, right? So if I did log of 3, because I don't have the fancy, log base feature here, which is just real unfortunate. Log of 3 divided by, we said we'll do 3 decimal places. Log of 1.00, my goodness, this thing is going slow, 5, right? Close it off. As you could already tell, that number is drastically different from the last time, right? And if I divide now by 12 to finish solving, let's see how off the years are. I went from 16.947 years to 18.3559 years. That's drastically different. That's almost a year and a half difference. So you can see how important the YORO is in these problems. Yeah, sometimes, the rounding doesn't make a huge difference, but in this case, it did, okay? Real big difference. All right, nice. Let's keep it moving. Lovely. All righty. We got Harry Styles jumping in the mix. I've been in the hip-hop game. I'm branching out, right? Harry Styles is also joining in the investments, and he has only one direction that he wants his investments to go, which is up. Duh. No one invests with the plan of going down. We want it to go up, make that money. He plans to invest in an account that compounds interest quarterly and wants his investment to double in 7 years. So he has a little time frame here, but he wants it to double. What annual interest rate would he need to make this happen? So now we're solving for the rate. Again, what formula are we using? We're using this one right here. Boom. All right. I am using green the entire time because we're talking money. I haven't changed colors yet. I'm not going to. All righty. So he wants his investment to double. So this is kind of like the last problem where we don't have an amount of money. It's rather ambiguous, but we don't really need the amount of money. We can say it's $1. We can say it's $100, $1 million, whatever. The amount of time it takes to double is going to be the same. So I'm just going to pick 2 right here and 1 right here. Cool. And then it's 1 plus, I don't know my rate, but I do know that it's compounded quarterly. That's what it said there, right? Quarterly. Raised to the quarterly times the amount of time, which is 7 years. So now it's time to solve. Let's do it. Well, let's see here. At first, dividing by 1 would just give me, would still leave me with 2 equals this mess in here. That's 28. We can do a little simplifying right there. So how do we solve something like this? Because if I think about it, if I were to put this into log format, I'd have log base, and this would be my base of 2 is equal to 28. And that really doesn't get me anywhere because then I have a variable in my base of a log. And I'm not solving for an exponent, so that does make sense that the logs aren't going to help me here because logs help me solve for exponents. I'm dealing with the base in here. Well, I'm raised to the 28th power. Perhaps I could either pick a 28th root it, or maybe I just raise this side to the 1 over 28, and then I would do that over here as well, right? Because whatever I do to one side, I do to the other. And with exponent properties, I know that these would cancel out, becoming 1, and then I'd have 2 to the 1/28th power, I'll leave it as that for now, equals 1 plus r over 4. So now I'm going to pull up the calculator and, voice crack. I'm going to leave it. Pull up the calculator and let's do some algebra on the fly with our calculator here. Let's do it. Look at that. The thing, it even shut off on me, to save some power. All right, now we got it working. So what would I be doing algebraically? I'd be subtracting 1, and then I would be multiplying by 4 to solve, right? Maybe I will write that out. So I'd have 2 to the 1/28th power. Minus 1 is equal to r over 4, and then I would multiply both sides by 4. So I could actually just type this whole mess into my calculator, and that should give me my rate. Let's do it. 4 parentheses 2 raised to the, and unfortunately I have to use another set of parentheses. All because mine doesn't do the fancy little exponent thing. That's a real bummer, It's a real bummer. And then minus 1. Close them. And, here we go. Looks like 0.10. So that would be what? 10%. Also nice and easy to see if we're like, hey man, what's that? I'll just multiply it by 100. You don't really have to do that. You can usually just move it yourself. But I got 10.0256. So 10.026%. I can go with that. 10.026% once we've rounded it. Boom. That's the interest rate Mr. Harry Styles would need to make sure his investment doubles in 7 years. Nice. Now, there's one problem that we haven't done yet. We haven't used this formula yet, and I kind of forgot to put in there, so I'm going to make up a problem real quick, and then we're going to do it. All right, here we go. Whipped one up. So you just purchased your first car for $7,000. I decided not to use any celebrities here because I feel like this is actually pretty applicable to just your life. However, you now realize that a car decreases in value by roughly 8% each year. I just made that percentage up, but maybe it's something like that, right? When you drive the car off the lot, it's decreasing in value as you go, right? Your cars don't increase in value as you drive them because you're using them more, generally speaking. Classic cars set aside. How much would you be able to sell your car for in 5 years if this rate of decrease stays consistent? So what formula are we using from that initial set of formulas? Well, I had this A of T is equal to A naught is what we had there, times 1 plus or minus the rate raised to the amount of time. Okay, so the amount of years in this case. So in this case, when we have this plus or minus, since it's decreasing, it would be minus. So let's go ahead and plug in here. T is 5, so the amount of money or amount it's worth after 5 years. And it started at $7,000. 1 minus 0.08 raised to the 5 years. Let's find out what this thing's going to be worth. Let's plug it in. All right, and there we have it, folks. $4,613.57. 4,600, was it 13? I can't remember now.